Hey, good morning. This is going to be kind of a wide-ranging talk, given some of the presentations that we had this morning. I think it's going to touch on some of the same themes, and perhaps there's a little bit of a controversial slide at the end, just to get the discussion session going afterwards. All right. So, about Rubin, for those of you who come from a particle physics rather than astronomy background, Rubin Observatory is an attempt to build a very large camera. It's a 3 gigapixel camera with a very wide field of view. And our purpose is to observe the whole sky that is visible from our site in Azerbaijan twice a week. So this is a very large big data project for astronomy. We would like to go on sky anytime now. That would be great. We've had some delays with COVID, especially in the construction sites and with our contractors, but we're getting really close now. So this is the very exciting time to be involved in this project. This is a visual for the field of view. So the kind of diagram that you see there is the field of view of one kind of picture that the telescope will take, and the moon is to scale for that picture. So there's like 169 CCDs. It's a kind of really giant camera, and the optics are such that the field of view is very large. Astronomy is a little bit different from particle physics in the way that people interact with the data. Traditionally, there haven't been large batch processing type workflows. Astronomy analysis tends to be very iterative and interactive. People typing stuff in the command line on their laptops, both before major data processing and after major data processing. When LSST was conceived as a survey, the legacy survey of space and time, when that survey was conceived, I think some people believed that this would be like the particle physics experiment equivalent for astronomy. And in fact, people still call it an experiment in various parts of the projects. I would argue that it's actually somewhere in between the particle physics model and the traditional astronomy model. And this actually, I think, becomes quite interesting when we talk about what computing looks like for this type of science use. So I was asked to talk a little bit about our Google Cloud experience, and just to tell you how we kind of ended up there. Basically, initially the project was conceived to have an on-premises facility at NCSA. That was a very traditional single facility on premises compute center. Several things have happened en route. One of them is that both the UK and France have contributed significant amounts of computing resources in exchange for data rights. So the UK and France in between them are going to actually end up doing 75% of the data release processing for the survey. And there was a kind of like a funding model earthquake, and the data facility moved from the National Science Foundation side of the project to the Department of Energy side of the project, because we're founded by both of these major agencies. In fact, the US based on-premises data facility is now going to be at SLAC. During this transition between the NCSA and SF side and the SLAC DOE side, we actually didn't know where it was going to go. We had this idea that it was actually going to go to a DOE lab, but we didn't know which one. It wasn't up to us. And so for a while, we actually were heading into operations without a data facility up and running to receive. And so this is the origin of our what we call their Interim Data Facility, which has been now live for almost a year. On Google Cloud, actually more than a year. This is a real production environment. It's not like a prototype or a toy project or a supplementary project, hence without the parachute part. This is literally the current production deployment aimed at serving science users. And if you're going to say, lady, you haven't even been on Sky, how come you have science users? The answer to that is that we have a data preview program that is actually based on the Dark Energy Survey Collaboration simulated data and we have started serving a increasing number of what we call data preview delegates. This is early users from the community that are both being used to familiarize the community with our tooling, and also for us to actually see the kind of tooling and data products being used by real human beings a little bit ahead of time. The final user load for our data facilities and our data is estimated to be around 8,000 users. So that's the kind of target metric for our deployed services to be able to service that kind of user load. And in astronomy, user load is extremely spiked in time. You know, it's not like you get a steady trickle. You know, everybody waits until 3 days before the AAS meeting, and then everybody wants to look at their data. So the non-uniformity of load is also an interesting factor in all this. Now, I'm just kind of going to say to a spoiler alert, being on Google Cloud has been a terrific experience on every level. And we'll talk a little bit about later about why. It's worked so well that I have, we have been begging to stay on cloud for a variety of reasons. That's not, necessarily always possible, but we are now baselined to leave the science platform, the main science platform deployment, the main collection of services that are servicing data rights holders, science users. We are now proposing to leave that on Google Cloud permanently, even after Slack is online to take off the data processing load of the Google Cloud deployment. And so what is kind of in an interim data facility, there is essentially the data processing clusters. Our technical baseline is to use Panda because of the multi-site arrangement between the UK, the US, and France. And we actually also use Russia to transport the data backwards and forwards between those sites. And oh, I see a hand. Do you want to go for it now?
Might as well. Benedict.
Sorry, just a question about, so some of your stuff is staying in the cloud. I'm assuming all of that is low data bandwidth, or because you said it was the data, it didn't quite.
Yeah. Right. So that's a good question. So we are primarily giving actually the science users, we're going to leave them in the cloud, and they are high data bandwidth users. I mean, that is the only way that a science user has to get the data. We have also done, Rubin has very high latency requirements where data has to be available within 60 seconds to the data processing, to the end of the data processing chain. And that we have also benchmarked that on Google and is fine. The main reason that the bulk of the data storage, this isn't so much a bandwidth as a total data volume, is going to on-premises, is because of the actual cost of storing the data. The actual data storage dominates the model more than the compute model. And Richard is here, and I'm sure Richard Dubois will also give you further details on Slack about the profile. There's no technical issue with leaving everything on cloud. It's mostly a kind of funding kind of issue, and we'll talk a little bit about that in a bit. Where at LSC, we have developed our own high-performance database management layer, which is QServe, that also runs both on premises and on cloud. We have a data abstraction layer that also processes a data model that is also runs both on premises and on cloud. And the Rubin Science Platform, which is this collection of services that are oriented towards this iterative and ad hoc interaction that users have with astronomical data sets, is the part that is going to remain on cloud because the advantages of keeping that on cloud are really incredibly compelling and actually worth the cost differential. And I'll be around the discussion session if you want to talk to me more about this. Since the Science Platform is actually my baby, here's a screenshot of a completely in browser based experience. This leverages both JupyterLab and Firefly, which is the visualization platform developed by our IPAC team. And this is I think, an incredibly credible attempt to reproduce the ad hoc kind of computer analysis environment that astronomers are used to having on their laptops in a server-side, data-side computing architecture. Here's a bunch of the reasons why we do want to stay on cloud, and we will do so for the Rubin Science platform. Some of the arguments are fairly obvious. It has to do with the scalability and the elasticity. It is great to have your public users in a completely different security domain than your main data production facilities. It opens a whole bunch of potential synergies now that more of us are looking to cloud hosting data sets and services. The velocity on working in a cloud environment is phenomenal from the development point of view compared to working on premises. And this has just nothing to do with the quality of the on-premises facility. This has to do with the fact that those facilities have been designed from the ground up to be self-serve from the developer's point of view. If you need more disk space, you don't have to go and file a ticket and ask somebody for more disk space. That's kind of pretty much there. We have found that generally architecting to a cloud environment has actually increased our portability rather than reduced it. And I can talk about that in the discussion session because I usually get questions about that after this kind of talk. And this is certainly not cheap, but actually the value for money is actually fairly phenomenal. So there are technically no reasons we can't do any of this kind of workflows in a commodity cloud environment. All right, so as I'm running out of time, here is the kind of food for thought slide. We can maybe discuss some of this later, and you can argue with me. But I thought I would actually write something about both how we actually see the Rubin model evolving, and also what I think. These are my kind of crystal ball predictions about the kind of the way the scientific computing is moving in the light of these developments. Number one, cloud bursting. We heard about that already once today. Cloud bursting, I think, is an extremely viable and compelling model. This is a model in which you do not size your on-premises infrastructure for peak loads, but you actually service peak loads by actually bursting into a cloud provider. And of course, the kind of multi-site data processing infrastructure using something like Panda and Rusio, places you reasonably well for that model. It's very hard for me to believe that 20 years from now we're still going to be building on-premises computing facilities. That's my wild prediction here, and my long bet. And so I think being able to develop our systems in a kind of cloud-friendly, cloud-native, cloud-first way is going to be quite critical. We have found that a lot of the kind of technology stacks that we use for the Rubin Science platform and other data kind of analysis, data science type services have huge commonalities with the stacks being used, generically, either by kind of Facebook engineers or by either scientific domains. There is incredible tooling that is both available now and emerging to allow people to do this kind of workflows in the cloud environment. Even in the 1 year that we have been on Google, we have had significant improvements of our infrastructure free to us, so to speak, that just came along as we were working on other things. We have also been looking strongly at this whole service collocation with the data. So if you have multiple data centers, so if you have a data center in France, in the UK, and the US, instead of trying to get the data all back together in order to serve it or try to federate it, what you do is you deploy services at each site. And then they're next to the data, they're highly portable. Kubernetes being our reference platform has been superb for that. And that allows you to send the user to where the data is in a very kind of transparent and efficient way. All right, and that's it. I thought I'd leave you a slide for the on-premises infrastructure, since I know a lot of folks are also interested in that. I see a hand up, and then I'm going to surrender my slots so that the next speaker can get going, and I will answer all the questions I've seen on go up on Zoom. Igor.
Can somebody unmute Igor?
Okay, yeah. So you're talking cloud, but then you mentioned Kubernetes. Did you use really just JKE and the Kubernetes layer, or have you used the whole anything else that is cloud that you got from Google?
Yeah, that is an excellent question. So we are very Kubernetes first architecturally, especially in the services side. But we actually use a wide variety of the kind of standard cloud technologies. For example, we use object stores for data storage. These are accessed through our Butler data abstraction layer, which actually doesn't care whether you're storing on a POSIX on some giant GPFS cluster or on a Google on a Google bucket. So we definitely use that. We make use of ad hoc services that Google provides. For example, if we need a relational database for programmatic reasons, as opposed to a very high performance data database, we will use Cloud SQL or whatever is available. And then on premises, we ask the provider to match that interface so that we can actually do it. I have seen, my team has not done that. I have seen other people use things like Cloud Run. We are potentially interested in some of the GPU capabilities, which are not part of our technical baseline, but I think our community is going to be interested in doing those. Yes, so, BigQuery is interesting. BigQuery is not a product that was available when we launched our own in-house high-performance database layer, but it's clearly a product in the right space. And in fact, we have put a TAP server, which is the table access protocol for astronomical data, in front of BigQuery. Our Google colleagues did that. That was a very successful experiment. So yes, it is. Kubernetes is definitely the key. But it is not the only thing that we're using. And I believe actually, and Richard will correct me, that some of the data processing flows actually use virtual machines rather than containers.
Yeah, it essentially leans to what Rob also asked. What would you miss if you just had an on-prem Kubernetes cluster?
Right. So since I've worked in both models, I can definitely answer this question. There are two reasons. Well, there are many reasons, but the two main reasons that it's actually a lot better working on cloud than on on-premises infrastructure is, like I said, the self-serve model is extremely powerful. I heard earlier one of our speakers talking about how he had to negotiate for disk space and this kind of thing. If I have to file a ticket to get something done, that is some hours that I have to wait for this ticket that I would not normally wait. But that's kind of more of a kind of project management reason. The real technical reason is that the level of developer support services in the cloud environment is superb, is increasing all the time, is being improved all the time, and it completely outstrips the ability of an on-premises team to actually provide the equivalent. For example, and I'll give you this example, which seems like minor and pedantic and nothing to do with exciting science. However, just in the year that we have actually been operating on Google Cloud, the log viewer went from log viewer to log explorer. This is the ability to the service that Google provides that allows you to actually look at the logs of your services as captured by Kubernetes. This has been a tremendous improvement in our ability to drill down and understand errors in our services and our architecture, and it's way better than the kind of traditional ELK structure, which, by the way, is really hard to get right on premises, and we got it for free. We didn't ask for it, we didn't spec it, but this is an improvement that happened as part of the evolving infrastructure services at Google, and Google isn't special here. I mean, I'm sure Amazon and Azure do the same. But basically, this continuing level of improvement in developer-facing services is actually superb. On premises, you spec a data facility, your data center will provide it for you, but you don't see that level of continuous improvement because, on-premises facilities just aren't staffed to have 200 DevOps engineers creating new developer-facing services. So that is the main the main kind of improvement for us. And then, of course, the elasticity and the scalability, which actually do impact how we service the users. My argument is that if you actually design your on-premises facilities to be like cloud-like, you do provide Kubernetes, you do provide object storages, then you have the portability and you can actually mix and match or have your services deployed in whichever model is appropriate to your funding model. So I think the right solution here is to make on-premises look more cloud-like to the extent possible. I feel like I've gone over my time limit, so I will stop
yes,
so that the next speaker can start, and I will see you in chat and in the discussion period if anybody wants to keep abusing me.